Good day. Today I will be discussing with you another topic in machine elements. In our previous discussion, we tackled about rolling contact with special emphasis given to rolling cylinders and rolling cones. Today I will be discussing with you about gears. The earliest known reference to gear or gear train is in a treatise by Hero of Alexandria during the 100 BC. You can see here in this presentation the odometer that he created. It is a device that is used for indicating the distance traveled by a vehicle. Gear trains are widely used in all kinds of mechanisms and machines, from openers even to aircraft carriers. Whenever a change in speed or torque of a rotating device is needed, a gear train or one of its cousins, the belt or chain drive mechanism, will be used. Gears of various sizes and styles are readily available from many manufacturers, as you can see here in this presentation. Assembled gearboxes for particular ratios are also stock items. The kinematic design of gear train is principally involved with the selection of appropriate ratios and gear diameters. A complete gear train design will necessarily involve considerations of strength of materials and the complicated stress states to which gear teeth are subjected. This lesson will not deal with the stress analysis aspect of the gear design. The simplest means of transferring rotary motion from one shaft to another is through a pair of rolling cylinders. They may be an external set of rolling cylinders as shown here in this animation, or it can be an internal set as shown here in this another animation. Provided that sufficient friction is available at the rolling interface, this mechanism will work quite well. There will be no slip between the cylinders until the maximum available frictional force at the joint is exceeded by the demands of the torque transfer. A variation on this mechanism is what causes your car or bicycle to move along the road. Your tire is one rolling cylinder, and the road the other. A very large radius is another cylinder. Friction is all that prevents slip between the two, and it works well unless the friction coefficient is reduced by the presence of ice or other slippery substances. In fact, some early automobiles had rolling cylinder drives inside the transmission, as though some present-day snow blowers and garden tractors that use a rubber-coated wheel rolling against a steel disc to transmit power from the engine to the wheels. A variant on the rolling cylinder drive is the flat or V-belt as shown here. This mechanism also transfers power through friction and is capable of quite large power levels, provided enough belt cross-section is provided. Friction belts are used in a wide variety of applications, from small sewing machines to alternative drive on your car to multi-horsepower generators and pumps. Whenever absolute phasing is not required and power levels are moderate, a friction belt drive may be the best choice. They are relatively quiet running, require no lubrication, and are inexpensive compared to gears and chain drives. A constant velocity transmission, as used in a number of automobiles, is also a V-belt and pulley device in which the pulleys are adjusted in width to change the ratio. As one of the pulley widens, the other narrows to change the relative radii of the belt with the respective V's. The belt circumference, of course, remains the same. Both rolling cylinders and belt or chain drives have effective linkage equivalent as shown here in this presentation. These effective linkages are valid only for one instantaneous position, but nevertheless show that these devices are just another variation of the 4-bar linkage in disguise. The principal drawbacks to the rolling cylinder drive or smooth belt mechanism are its relatively low torque capability and the possibility of slip. Some drives requires absolute phasing of the input and output shafts for timing purposes, A common example is the valve train drive in an automobile engine. The valve cams must be kept in phase with the piston motion or the engine will not run properly. A smooth belt or rolling cylinder drive from the crankshaft to camshaft would not guarantee correct phasing. In this case, some means of preventing slip is needed. This is usually means by adding some meshing teeth to the rolling cylinder. They then become gears as shown here in this presentation and are rolling together called gear set. When two gears are placed and meshed to form gear sets such as this one, it is conventional to refer to the smaller of the gears as the pinion and the other gear as the gear. By the end of this lesson, you should be able to identify the various terminology used in kinematics of gear tooth theory, gear types, and the kinematic design of gear sets and gear trains of simple, compound, and epicyclic or planetary types. Define the gear ratio, circular pitch, base pitch, pitch diameters, center distance, addendum, dedendum, hole depth, clearance, outside diameters, and contact ratio of a gear set with a given parameters. Design the gear set given velocity ratio and solve the velocity ratio given the gear set configuration. This will be the outline of my presentation. So let's start first with the basic of all, which is the fundamental law of gearing. The fundamental law of gearing provides that the angular velocity ratio between the gear set remains constant throughout the mesh, which is a very important parameter because especially for very good timing, for example, this will require that the angular velocity ratio should be constant throughout the mesh. The angular velocity ratio, based on the fundamental law of gearing, is defined as mv, which is equivalent to the ratio of the output angular velocity to the input angular velocity. In our previous discussion about rolling contact, we learned that this is proportional to the radius and eventually to the diameter, as you can see here. As a consequence also of fundamental law of gearing is a torque ratio, which is just the reverse of the angular velocity ratio. As you can see here in this presentation, we can already see a relationship between angular velocity ratio and torque ratio based on these equations by rearranging them. The gear set therefore is a device to exchange torque for velocity and vice versa. Because if you can observe, for example, the rotation of a shaft, for example, is then converted to velocity, whether it's linear or angular velocity. Torque ratio is just the reciprocal of the velocity ratio. The mechanical advantage, on the other hand, is equals to the torque ratio. The mechanical advantage tells us how much you are able to change the given velocity to the required velocity. Now that we learned the fundamental law of gearing, we will use this principle in designing the involute tooth. The involute gear profile is the most commonly used system for gearing today, with cyclode gearing still used for some specialties such as clocks. In an involute gear, the profiles of the teeth are involutes of a circle. When we say involute, it is a curve that can be generated by unwrapping a taut string from a cylinder called the evolute. Say for example, you have here in this animation. The involute uses a string which is always tangent to the cylinder, as you can see here in this animation. The center of curvature of the involute is always at a point of tangency of the string with the cylinder. A tangent to the involute is then always normal to the string, the length of which is the instantaneous radius of the curvature of the involute curve. So to illustrate how to draw the involute, say for example you have here a base circle and you would like to draw the involute between points A and E. So the involute tooth form can be drawn first by dividing the arc from A to E into equal arcs. So here I divided it into 4 arcs. We have AB, we have A to C, A to D, and A to E. Once you divided it, you are going to draw vertical lines with respect to this. Not vertical, but tangent lines with respect to the points. So you can see here we have a tangent line from point B, a tangent line from point C, a tangent line from point D, and finally we have a tangent line from point E. Now we're going to measure the length of the arc, say for example AB, and we project it into that tangent line so that it will be the BB prime. Same also with AC, we measure that and then we project it into the tangent line. That's why we have here CC prime. And then we also do that for D. We measure AC. So take note that we measure this arc here and then we project it here in the tangent line. So that's why we have AD is equals to DD prime, and finally AE is equals to EE prime. And then you take note of those points, and then this now represents the involute tooth form. So this will be the profile of the tooth that we will draw for example for the gear. The good thing about the involute tooth form is that it obeys the fundamental law of gearing. So again, to measure the distance AB, it is equals to BB prime. So take note that you are measuring the arc, not a line but an arc here, AB. You can use, for example, a protractor or whatever device. Then we have AC is equals to CC prime, AD is equals to TT prime, DD prime, and then we have AE is equals to EE prime. So that's basically how you can draw the involute. So we have here some terminologies that we will encounter in the succeeding presentation. The first one is what we call the base circle. The base circle is the cylinder from which the strings of this involute are unwrapped. So when you draw the involute, so the basis for drawing them is in the base circle. The addendum, on the other hand, is the amount of tooth that sticks out above the pitch circle. So pitch circle will be defined later, but the addendum is the amount of tooth that go beyond that pitch circle. And then we have here another term, axis of transmission, is an axis which always passes through the pitch point, which we'll also define later, regardless of where in the mesh the two teeth are contacting. So it is always like that. So take note of these terms. So to locate them, for example, here in this diagram, it shows two involutes on separate cylinders in contact or in mesh. This contact represents the gear teeth. So we have here also the different parts of this involute. So this red line or circle here represents our base circle. So these two circles now represents our base circle of gear, this bigger one, and then the smaller one, since the smaller is the pinion, then this is the base circle of the pinion. So when you draw the the involute or the tooth form, it should be from this base circle. So later on, when you design, for example, a tooth, a gear, then you will draw the involute with respect to the base circle. So these are the base circle. And then this blue circle here represents the pitch circle. So we have the pitch circle for our gear, so the bigger one, and then we have the pitch circle for the pinion. And then this line here, which is tangent to the base circle, as you can see, it forms 90 degrees to both the meshing gear teeth. So also at 90 degrees, therefore it's tangent to the red circle or the base circle. This represents our axis of transmission. And the difference between the upper part of a teeth and then the pitch circle is the addendum, so it's the excess. Same also for the addendum of our pinion. So in the design, they are actually equal, but since we also include some clearance, then here that's why they have some quite difference in the measurement of the addendum. Therefore, we can restate the fundamental law of gearing this way, that the common normal of the tooth profiles at all contact points within the mesh must always pass through a fixed point on the line of centers called the pitch point. So this mesh should always pass through the pitch point. So to locate the pitch point, you can see here another pair of involute tooth forms in two positions, just beginning contact and about to leave the contact. The common normals of both these contact points still pass through the same pitch point. It is this property of the involute that causes it to obey the fundamental law of gearing. Therefore, the ratio of the driving gear radius to the driven gear radius remains constant as the teeth move into and out of the mesh. So the pitch point here is located here. So this is our pitch point. So this is also located at the intersection of the two pitch circles between the two mating gears. The points of beginning and leaving contact define the mesh of the pinion and the gear. The distance along the line of action between these points within the mesh is what we call the length of action, or denoted here by Z. So this length of action Z is the distance along the line of action, which we all defined earlier. So this is our length of action. It passes through the line, the axis of transmission, also defined by the intersection of the respective addendum circles with the line of action. So this is the length of action denoted by this arrow here. The distance along the pitch circle within the mesh is the arc of action. So this arc here, this red arc here, is what we call the arc of action. And the arc of action is equals to the sum of the angle of recess and the angle of approach. So the angle subtended by these points in the arc of action and the line of centers are the angle of approach and the angle of recess. So it denotes the points of beginning and leaving contact between the meshing pinion and the gear. So here is the point wherein they leave contact, and then we have here the point wherein they begin to have a contact. So along the pitch circle, the intersection is the arc of action. Again, the pressure angle, on the other hand, in a gear set is similar to that of the cam and follower as defined in the previous. It is defined as the angle between the axis of transmission or line of action and the direction of velocity at the pitch point. The pressure angles of gear set are standardized at a few values by the gear manufacturers. So based on the manufacturers, they define that the nominal center distance for the gear set as cat. So the standard values are 14.5 degrees, 20 degrees, and 25 degrees, with 20 degrees being the most commonly used and 14.5 degrees now being considered obsolete. Any custom pressure angles can be made, but it is expense over the available stack gears because the stack gears are manufactured in these standard values. With the standard pressure angles would be hard to justify. Special cutters would have to be made. Gears to be run together must be cut to the same nominal pressure angle also. So that's the disadvantage when you use other angles other than the standard pressure angles. So the pressure angle here is denoted by this angle C here. So this angle here is equals to this angle also here. So that is our pressure angle. So as you can see, the pressure angle passes through the line that is tangent to the axis of transmission to both the pinion and the gear. And then the normal to the pitch circle, which is this one. So that is our pressure angle. So for example, you will be designing a gear later on, then you are given with the pressure angle, then you should make sure that it will have a tangent, no, with respect to our axis of transmission to both the gear, the pinion and the gear. And it passes, the normal passes through the pitch circle. When involute teeth have been cut into a cylinder with respect to a particular base circle to create a single gear, we do not yet have a pitch circle, because pitch circle can only be formed when there is already a meshing of two teeth. The pitch circle only comes into being when we mate the gear with another gear to create a pair of gears, which we call the gear set. There will be some range of center to center distance over which we can achieve a mesh between the gears. There will also be an ideal center distance that will give us the nominal pitch diameters for which the gears were designed. However, limitations of manufacturing processes give a low probability that we will be able to exactly achieve this ideal center distance in every case. More likely, there will be some error in the center distance even if it is small. So what will happen to the adherence to the fundamental law of gearing if there is error in the location of the gear centers, as you can see here? If the gear tooth form is not an involute, then an error in the center distance will violate the fundamental law of gearing, and there will be a variation or ripple in the output velocity. So as a consequence of that, of course, we will not be able to achieve the timing that is required, for example, in the transmission. This is the principal advantage of the involute over the passable tooth forms, and the reason why it is universally used for gear teeth. So this is the reason why we designed the tooth using the involute tooth form that I illustrated a while ago, because even if the center distance have some error, it does not affect the velocity ratio. So that's one of the advantage of using the involute tooth form. This figure shows what will happen when the center distance is varied on the involute gear set. Note that the common normal still goes through a pitch point common to all contact points within the mesh, but the pressure angle, as you can see here, is affected by the change in the center distance. So the pressure angle here in the correct center distance is 20, and in the incorrect center distance, due to the increase in the center distance, the new pressure angle would be 23 degrees. So the pressure angle is affected by the change in the center to center distance, which affects also the timing. Another factor affected by changing the center distance is what we call the backlash. It is defined as the clearance between the mating gear teeth measured at the pitch circle. So increasing the center distance will increase the backlash, and the vice versa. As you can see here, this is the backlash, and it is located, measured at the pitch circles of the mating gears. So now that we learned the importance of the involute tooth form in the design of gears, as well as some of the important parameters, we are now ready to tackle the gear tooth nomenclature. Figure below shows two teeth of a gear with standard nomenclature defined. The pitch circles and the base circle have been defined in the previous discussion. So we can see here the base circle. So again, it is where we draw the involute. And then we have here the pitch circle. So this is equivalent, for example, in the contact of a rolling cylinders. So this is the circle there. This is where also we can locate the pitch point at the pitch circle. The tooth height is defined by the addendum and the dedendum that are reference to the nominal pitch circle. The dedendum, as you can see here in this presentation, is slightly larger than the addendum to provide a small amount of clearance between the tip of one mating tooth, which is the addendum circle, and the bottom of the toothpaste of the other, which is the dedendum circle. The tooth thickness, you can see here, on the other hand, is measured at the pitch circle. Tooth space width is slightly larger than the tooth thickness. The difference between these two dimensions is the backlash. So when you wanted to compute the backlash, you just subtract tooth thickness to the tooth thickness and tooth space. The face width of the tooth is measured along the axis of the gear. The circular pitch is the arc length along the pitch circle. Circumference measured from a point on one tooth to the same point on the next. The circular pitch defines the tooth size, so that's why it's an important parameter. So you can see also the other parts here in this gear tooth nomenclature. So the other tooth dimensions are standardized based on the dimensions as shown here in this table. So this is based on the American Gear Manufacturing Association. So this is the AGMA full depth gear tooth specification when you have coarse pitch and fine pitch. So we can use this table to specify the pressure angle, the addendum, the dedendum, working depth, hole depth, circular tooth thickness, fillet radius or the basic wrap, minimum basic clearance, minimum width of top length, and the clearance. So this is the tooth profile for the different pressure angles, 14.5 degrees, 20 degrees, 25 degrees based on the AGMA. So again, this upper portion here is the addendum, and then we have the dedendum at the bottom. So let's define the circular pitch. So the circular pitch is defined, denoted by the symbol PC, and is defined as pi d over n, where d is the pitch diameter or the diameter of the pitch circle, and then we have n is the number of teeth. The base pitch, on the other hand, is PC cosine of our pressure angle. Then we have the diametral pitch, denoted by the symbol PD, is equals to the number of teeth divided by the pitch circle diameter, or the D. Or based on our previous equation, it can be also written in terms of pitch circle, circular pitch, which is pi over PC. So the unit, on the other hand, we have module. So module is just the reverse of the diametral pitch. So that's why it can be written as the diameter over the number of teeth. The units of module are in millimeters. On the other hand, the PD is in inches. Unfortunately, metric gears are not interchangeable with US gears, despite both being involute tooth form, as their standardized for tooth sizes are different. In the United States, gear tooth sizes are specified by diametral pitch, elsewhere by module. So the conversion from standard to the other is given by this formula. So you can convert, say for example, you are given with diametral pitch in inches. To convert it to module, you will use this formula. Then we have the contact ratio, which is defined as the average number of teeth in contact at any one time. So say for example, you wanted to compute how many teeth will be in contact at any time, then you can use this contact ratio formula denoted by Z over PB. Z is the length of action, which we also discussed in the previous slide, and that can be, the length of that can be computed using this very long formula here in terms of the radius of the pinion and the gears and the pressure angles. The velocity and torque ratio can then also be defined in this formula in terms of diameter and also the number of teeth. So this N here is actually the number of teeth and D is the pitch diameter. So note that the minus sign implies an external gear set. So when you have a minus sign, and a positive sign denotes an internal. So positive external, minus external, positive internal. So again, our velocity ratio is just the reverse or reciprocal of the torque ratio. And they can also be related to the pitch diameter and the number of teeth. So now that we know the different gear tooth nomenclature, we can now proceed to interference and undercutting. The involute tooth form is only defined outside of the base circle, if you can still remember. In some cases, the dedendum will be large enough to extend below the base circle. If so, then the portion of tooth below the base circle will not be an involute and will interfere with the tip of the tooth on the mating gear, which is an involute. If the gear is cut with a standard gear, shaper, or a hub, the cutting tool will also interfere with the portion of tooth below the base circle and will cut away the interfering material. This results in an undercut tooth as shown here. So we have here an undercut tooth. So when we extend the involute below the base circle, so since this circle here represents the base circle, this undercutting weakens the tooth by removing material at its root. The maximum moment and maximum shear from the tooth loaded as a cantilever beam both occur in this region. Severe undercutting will promote early tooth failure. That's why it must also be avoided. Interference and undercutting caused by manufacturing tools can be prevented by simply avoiding gears with too few teeth. So if a gear has a large number of teeth, they will be small compared to its diameter. As the number of teeth is reduced for a fixed diameter gear, the teeth must become larger. At some point, the dedendum will exceed the radial distance between the base circle and the pitch circle, and interference will also occur. So as a resolution to that, we have here a table which shows the minimum number of pinion teeth that can mesh with a rack without interference as a function of the pressure angle. The minimum number of teeth that can be cut by a hub without undercutting as a function of pressure angle is also shown here. So we have here the minimum number of pinion teeth to avoid interference between a full depth pinion and a full depth rack. So we actually have that pinion and rack, and we can have a minimum number of teeth based on the design pressure angle. So for example, the pressure angle is 20 degrees. The minimum number of teeth in the pinion should be 18. That is to avoid undercutting or interference. To avoid interference. For the minimum number of pinion teeth to avoid undercutting when cut with a hub, we can also use this table here. Say for example, you have a pressure angle of 25, then the minimum number of teeth to avoid undercutting would be 14. For the maximum number of gear teeth on the other hand, which is the larger of the mating gears, to avoid interference between a 20 degrees full depth pinion and a full depth gears of various sizes, we can have also this table to get the number of pinion teeth and the maximum gear teeth equivalent to that. Same also for 25 degrees. Profile shifted teeth with long and short addenda to avoid interference and undercutting is shown here in this diagram. So let us have an example for us to understand the different gear tooth nomenclature. So here we are to confine the gear ratio, circular pitch, base pitch, pitch diameters, center distance, addendum, dedendum, hole depth, clearance, outside diameters, and contact ratio of a gear set. With the given parameters, we have diametral pitch of 6, pressure angle of 20, 19 tooth pinion mesh with a 37 tooth gear. So we are given with the diametral pitch, the pressure angle, the number of tooth on the pinion, and the number of tooth on the gear. And we are looking for the gear ratio denoted by mg. We have circular pitch, base pitch, we have pitch diameters of both the gears and the pinion, the center distance, the addendum, the dedendum, the hole depth, clearance, the outside diameter of the pinion, and also with the gear, the contact ratio of the gear set. So once we have this value, and since we already know how to draw the involute tooth form, then basically we can draw the tooth using SolidWorks, for example. So what you're going to do is just to draw one meshing teeth from the pinion and the gear, and then you just mirror it using the features mirror of the SolidWorks. So the gear ratio can be computed using the formula NG over NP. So since the number of gear tooth on the gear would be larger than that of the pinion, since it's the larger one, then we would have a value greater than 1. So the gear ratio is 1.9474. Then for the circular pitch, it's defined as pi over PD, and PD is given, it's 6. So that's why our circular pitch is 0.5235 inch. And then we have the base pitch. So the base pitch is PC cosine of our pressure angle. So that is equals to 0.4920 inch. So our base pitch is 0.4920 inch. So we already have the gear ratio mg, we have the circular pitch PC, and then we have the base pitch, which is PB. Then we have the pitch diameter of the pinion. So this is to draw the pitch circle. Since we have the pitch diameter, then we can draw the pitch circle for the pinion, and that is just our number of teeth in the pinion divided by the diametral pitch. So substituting the value, our pitch diameter of the pinion is 3.166 inch. So you can draw a circle that will be the pitch circle for the pinion if you use this diameter. For the gear, on the other hand, that is NG over PD. Substituting the value from the given, we can get the pitch diameter of the gear, and the value is 6.1667. So take note that the contact of the pitch diameter of the gear and that of the pinion is the pitch point based on our previous slide. So now you can already draw the pitch circles based on this pitch diameter of the pinion and the pitch diameter of the gear. The nominal center distance, on the other hand, is the sum of the pitch radii. So that is just Rp plus Rg. So we can also compute now the nominal center distance, which is 4.667 inch. So therefore, this is the center to center distance of the shaft of these two gears, for example. And then we will solve now for the addendum. So addendum is just the portion of the tooth that extends above our pitch circle, Since we already have the pitch circle, then we need to compute the addendum so that we can draw the upper portion of the teeth. So the addendum is defined in our AGMA standard table as 1.0 divided by PD. So the addendum would be equals to 0.1667 inch. So the addendum is 0.1667 inch. So again, this is the same for both the gear and the pinion. So now you can draw that addendum since you already have the pitch circle. And then the dedendum, on the other hand, is denoted by B. That's 1.25 over PD. So it's larger than the addendum so that we can have clearance. So the dedendum is 0.2083 inch. So this is already the bottom portion of our gear tooth. So the whole depth or the height of the teeth would be the sum of A and B. So that is A plus B. So we can already have the whole depth of the tooth. So the whole depth is 0.375 inch. So by this time, we can already trace the gear tooth using the involute tooth form, if you can still remember how to draw that. And then you just measure the addendum and dedendum from the pitch circles. Then you can also draw that to obtain a trace already of the gear tooth. The clearance, on the other hand, is just the difference between the dedendum and the addendum and the dedendum. So that is 0.0416 inch. So the clearance is 0.0416 inch. The outside diameter of the pinion is the pitch diameter plus the two addenda. So if, say for example, we are going to draw the complete outside diameter of the pinion, then the outside diameter is just the pitch diameter, which we already have, and the two addenda. You just add them. So the outside diameter of the pinion is equals to 3.5 inch. The same also for the outside diameter of the gear. It is just the pitch diameter plus the two addenda. So our outside diameter of the gear is 6.5 inch. Then we can now have the contact ratio, which is defined as Z over PB, or the base pitch. So the length of action Z is computed using this formula. So just substitute the value that we already computed. So the length of action is 0.7989. So take note that this is the length, the line that is from the connecting the initial contact of the gears, the tooth, and then the final contact. So this is the length of action, and it is measured from the axis of transmission. That length is 0.7989 inch. So the contact ratio is, since we already have the base pitch, is 1.62. So once you already have this parameter, you can also compute the rest of the parameters so that you can draw the complete gear tooth. And then you just mirror those gear tooth so that you can obtain the whole gears. So this will be our lab design in the coming days. So the average number of teeth in contact at any time is 1.62. So it's almost 2 gears contacting at any time. So now that we already know the interference and cutting and its effects on the gears, as well as the computation of the various nomenclature in gear tooth, now we can proceed to the different gear types. So the different gear types are, we have first the spar gears. The teeth are parallel to the axis of the gear for spar gears, as you can see here in this presentation. So this is the axis of the gear, and then the teeth are just parallel. They are the most common and can only be meshed if their axes are parallel. So when you mesh spar gears, their axis should be parallel also. Then we have helical gears. The helical gears has a teeth that are at helix angle with respect to the axis of the gear. So it runs quieter than spar gear. That's one of its advantage. And it is also stronger as compared to the spar gear. So the helix angle is the angle with respect to its axis. Then we have the cross-axis helical gears. So we can actually, unlike the spar gear, wherein we can only mate them when they have parallel axis, for helical gear we can actually mate them even if the axes are not parallel. So we can do that by using cross-axis helical gears. So as you can see, we can mesh with our axis at an angle which is not necessarily 90. So we can actually have it different kind of mesh, depending also on the helix angle. And then we have the herringbone gears. So the herringbone gear is just identical to the helical gear, it's just that it is formed by joining two helical gears of identical pitch and diameter but opposite hand and the same shaft. So as you can see here, we have two helical gears connected. They are used in large high power applications. So that's one of the advantage of herringbone gears. Then we have worms and worm gear. So this is the worm, and then we have here the worm gear. So if the helix angle is increased, then we can obtain the worm and worm gears. The worm has only one tooth, as you can see here, but this tooth is wrapped around, it's wrapped continuously around its circumference, no? Like a screw thread. So it resembles a screw thread for the worm. From the worm wheel, also known as the worm gear, it is the gear that is meshed with the worm. So this is a worms and worm gear. They are applied, for example, when a jack is used to raise a car, and also for jack and hoist applications. And then we have the rack and pinion. So the diameter of the base circle of the gear is increased without limit, it will become a straight line. So the linear gear is called the rack. So this will be the rack, this linear gear, and then this will be our pinion. So that's why we have rack and pinion. They are used in applications wherein it's required to convert rotary to linear motion or vice versa. Example is the rack and pinion steering mechanism of the automobile. Then we have the bevel gears. So the bevel gears are based on rolling cones. So our previous example of gears or gear types, they are based on rolling cylinders, if you can notice. But bevel gears are based on rolling cones, which we also discussed in the rolling contact. So they are used for connecting any angle between the shafts, including 90 degrees. So for right angle drives, cross helical gears or a worm set can be used. But for any angle, we can use the bevel gears. So if the teeth are parallel to the axis of the gear, it will be a straight bevel gear, as you can see here in this presentation. So this is an example of a straight bevel gear. So the angle between the axes of the cones and the included angles of the cones can be any compatible values as long as the apexes of the cones intersect. So if they do not intersect, there would be a mismatch of the velocity at the interface. So the incorrect arrangement would be just like this, which would cause velocity mismatch if the apexes do not intersect. So this should be the correct arrangement wherein the apexes should be coincident both for internal and external contact bevel gears. So we also have a spiral bevel gear, which is used if the teeth are angled with respect to the axis. So we have here spiral gears, a spiral tooth for the spiral bevel gears. So if the axes between the gears are non-parallel and also non-intersecting, the bevel gears cannot be used. Therefore, we will use another one, which is the hypoid gears. So they are used for non-parallel and non-intersecting axes between the gears. So they are based on rolling hyperveloids of revolution. So application of these are on final drive of front gear as well as in rear wheel drive automobile among others. So these hypoid gears are used in the final drive of a front engine, rear wheel drive automobiles in order to lower the axis of the drive shaft below the center of the gear axle to reduce the drive shaft hump in the back seat. So this is how it looked like. So again, it's based on the rolling hyperveloids of revolution. So as you can see, the axes are non-intersecting and non-parallel at the same time. Then we have non-circular gears. So they are based on rolling centroids. So they are applied, for example, on printing presses where variation in the angular velocity of roller is required on a cyclical basis. So now that we already learned the different gear types, we can now proceed to the last part of this lesson, which is the gear trains. A gear train is any collection of two or more meshing gears. A single gear set of spar, helical, or bevel gear is usually limited to a ratio of about 10:1, simply because the gear set will become very large, expensive, and hard to package. It is common practice to insert a single idler to gear to change the direction, but more than one idler is superfluous. There is little justification for designing a gear train. If the need is to connect two shafts that are far apart, a simple train of many gears could be used, but will be more expensive than a chain or belt drive for same application, because most of the gears are not expensive. So one type of gear train is what we call the simple gear train. So here each shaft carries one gear. As you can see here, each of the shaft carries one gear of different diameters. Simple gear train's velocity ratio can be computed using this formula. So if you wanted to get the gear train's velocity ratio, it is just the ratio of the number of teeth for the input gear to the number of teeth of the output gear. So if, for example, you have here an input gear N2 and then we have an output gear N6, then the gear train's velocity ratio would just be the ratio of the last, which is the output, and the input. So the velocity ratio for simple gear train is again limited to 10:1 for design consideration. Then we have the compound gear train. So they can be used for velocity ratio greater than 10:1. So at least one shaft carries more than one gear. As you can see here, we have shaft. This input shaft carries one gear. And then we have this idler here that carries two gears. And then we have the output shaft that carries one gear. So this is already considered as a compound gear train. So this would be the the upper view, and then we have here the side view of this compound gear train. So this is the input and then we have the output here. So for the Compound gear train's velocity ratio, it is just computed using the formula, the product of the number of teeth on the driver gears, and then divided by the product of the number of teeth on the driven gears. So the plus minus sign here is just whether it is clockwise or counterclockwise. Also take note that the number of teeth is also related to the diameter or the radius. So if the number of teeth is not given, but you are given with the number of teeth, the number of diameter, then you can use the relationship that is shown in the previous slide to compute the compound or simple gear train's velocity ratio. And then we have here another one, because the conventional gear trains described in the previous section are only limited to 1 degree of freedom, but there are instances when we need higher degrees of freedom devices. So another class of gear train that has wide application in that is the epicyclic or the planetary gear train. So this is a 2 degrees of freedom device wherein 2 inputs are needed to obtain a predictable output. So sun gear and planet gear are orbiting around the sun, and they are held in orbit by the arm. So we have here the sun gear, the smaller one, and then we have here the output gear, which is the planet gear, and they are held together by the arm. So our inputs here are the angular velocity of this sun gear as well as that of the arm. And then the output would be the rotation here of the planet gear. So this is already a planetary gear. A more useful configuration of the planetary gear is shown here in this slide. So which is a ring gear, wherein a ring gear is added. So this ring gear, the ring here at the outer portion, is it meshes with the planet and pivots at 0, 2 at the center here. So it can easily be tapped as the output member. Most planetary gear trains will be arranged with a ring gear to bring the planetary motion back to a grounded pivot. So take note that the sun gear, ring gear, and the arm are all brought out as a concentric hollow shaft so that each of them can rotate. So this is how they can look like. So we have here the sun, the planet, the arm, and then we have here an addition, which is the ring gear. So the angular velocity of the ring gear can be computed as the angular velocity of the arm plus the angular velocity of the gear and with respect to the arm. Let us have another example. So we are to design a compound gear train for an exact train ratio of 180:1. So we are looking for a combination of gears that will give us a ratio of 180:1. So the first step is to determine how many stages or gear sets are necessary. Simplicity is the mark of a good design. So I'll try the smallest possibility first. We can do this by taking the square root of our 180, which is our given gear ratio, which is 13.416. So 2 stages each of 13.416 will give approximately 180:1. However, this is a larger ratio than our design limit of 10:1. So take note that if we have a simple gear train, then the ratio of a single stage should be 10:1. If we use 13.416, it would be larger than that. So it would not be sufficient to have a 2-stage. So therefore we will try the 3 stages by taking the cube root of 180, which is 5.646. So as you can see, this is already below the 10:1 requirement. So 3 stages will do. If you can find some integer ratio of gear teeth that will yield 5.646:1, we can simply use 3 of them to design our gearbox. Using a lower limit of 12 teeth for the pinion and trying several possibilities, we get the gear set shown in table as possibilities. So the lower limit of 12 is chosen because of our undercutting and also interference consideration. So the possible gear sets for 180 is the one if we have 3-stage compound train is shown here. So we have the possible gear set ratio, which is 5.646. The pinion teeth, which is wherein we will choose a lower limit of 12, and then we have the resulting gear teeth. So if, for example, you have a gear ratio of 5.646, so if you have a pinion teeth of 12, then you can get gear teeth of 65.75 by multiplying them, and so on and so forth. So the number of gear teeth obviously must be an integer. So the closest to an integer in this table here is 79.05. So thus a gear set with 79:14 gear set comes closest to the desired ratio. So therefore we can say, for example, choose a gear teeth of 79 and a pinion teeth of 14, since this is the number that gives us the gear teeth, which is almost a whole number and closest to the desired ratio, which is 5.646. So applying this ratio to all 3 stages will yield a train ratio of 79 is to 14 multiplied by 3, so that is 179.68 is to 1. So which is within 0.2% of the required 180 is to 1. So this may be an acceptable solution provided that the gearbox is not being used in a timing application. If the purpose of this gearbox is to step down the motor speed for a crane hoist, for example, an approximate ratio will be adequate. But if it is used for a gearbox which is required in a timing application, then this may not be acceptable. So if it is the case that it is not for timing application, then we can use 3 stages of gears which has a train teeth ratio of 79 for the gear and pinion 14. So we just have 3 stages of equal this ratio here, which is 79 is to 14. However, many gearboxes are used in production machinery to drive camshafts or linkages from a master drive shaft and must have the exact ratio needed, or else the driven device will eventually get out of phase with the rest of the machine. If that were the case in this example, then the solution found in step 3 would not be a good solution. We will need to redesign it for exactly 180 is to 1. Since our overall train ratio is an integer, it will be simplest to look for integer gear set ratio. Thus, we need 3 integer factors of 180. So the first solution above gives us a reasonable starting point in the cube root of 180, which is 5.646. So if we round this up or down to an integer, we may be able to find a suitable combination. So 2 compounded stages of 6 is to 1, since we round off the 5.646 higher, then we would have, if we choose, for example, 2 compounded stage of each 6 is to 1 gives us, this combination gives us a ratio already of 36, because we just multiply them basically. So we have 6 times 6, so we have a ratio of 36. And since the requirement is 180, so we divide 180 by this 36 so that we can obtain 5. Thus, the stages shown here in this table provide one possible exact solution. So this would be the exact solution for 180 is to 1, 3-stage compound train, and this will be the gear set ratio, which is 665, and the pinion gear teeth corresponding, as well as the gear teeth corresponding. So take note that we chose 14. So this solution meets our design criteria. It has the correct exact ratio, which is given in the table in the previous slide, and the stages are all less than 10 is to 1. So the ratio of the teeth of each of the stages is less than 10:1, which is 6:1. And no pinion has less than 14 teeth, which avoids undercutting if we use 25 degrees pressure angle gears. So if we're going to rearrange these gear set, then we can have this solution here. So we have the shaft here, which has 14 teeth, and then we have, this is our pinion, and then we have connected it to a gear of 84, and then we compounded it with another 14, and then mesh it with 84 also, this in the same way, and then we all compounded this with 14, and we mesh it with 70. So these are the three stages here in order to obtain the desired exact train ratio of 180:1. So take note that for the design, it actually has a lot of answers possible, but the answer should meet the criteria. So here the criteria is that the stages are all less than 10:1. As you can see, 84 to 14 is less than 10:1 if you get the ratio of that. Same also with 70:14 here in the last stage. And then the no pinion here have less than 14 teeth, as you can see, to avoid undercutting. So that is how you can design a compound gear train. So we can check and verify the gear ratio to be 1/180 or 180:1. So multiplying the number of teeth in the driven gears, which is not driven but the drivers, which is 14 here. This is the driver, and for here this is the driver, and this 14 here is also the driver. So that's why 14 by 14 by 14. The driven gears are the gears which has 84 teeth here and the 70 here, and the last are the output shaft. That's why we have 84 by 84 by 70. Then we have another example. So in the figure, the number of teeth on each gear is as indicated with a T. Find the speed of a shaft C if the speed of A is 25 RPM. So we are given here with a compound gear set. So we have shaft A, shaft B, and shaft C. Then we have, for shaft A, we have a gear of 100 teeth. And then for shaft B, we have a compound gear which has 125 teeth and another one which has 50 teeth. So the 50 teeth is meshed with the 100, and then the bigger one is meshed with the 25 teeth in shaft C. So the compound gear train's velocity ratio can be computed using the formula product of the number of teeth on the driver gears divided by the product of number of teeth on the driven gears. So for the driver gears, these are the gears that drives the driven. So we have the 100 and then the 125. That's why we multiply them. And then the driven are the 50 and the 25. That's why we have here 50 by 25. So our compound gear train's velocity ratio for this given here is positive 10. So it's positive because, as you can see, we have a clockwise rotation for our input shaft. So the speed of shaft C can be obtained by using our ratio, which is our gear train's ratio, which is also equivalent to the output shaft angular velocity divided by the input shaft angular velocity. So substituting the values, since the input shaft has 25 RPM, then the output shaft speed is 250 RPM. So the speed of shaft C is 250 RPM clockwise. So you can verify the direction by examining by knowing that the rotation of the rolling cylinders. So that is 250 RPM clockwise for shaft C. So as you can see, we're able to achieve a higher speed by using gearing system from 25 RPM to 250 RPM. And then we have here another figure wherein the number of teeth on each gear is indicated also. Shaft A turns 25 RPM clockwise. We are going to find the speed of shaft C. So this time we have a simple gear train. There's no shaft that contains two gears. So the solution would be, for the simple gear train's velocity ratio, it is just equals to positive minus of the number of teeth of the input gears, and then we have the number of teeth of the output gear. So the input here is this 100T, and then the output is the 25T. So basically this 75T is just an idler in order to change the direction of the gear. So the simple gear train's velocity ratio, substituting the input and the output RPM, is positive 4. So to obtain the speed of shaft C, we'll then use our velocity ratio formula using the fundamental law of gearing. Then we can get the speed of shaft C to be 100 RPM. If you're going to examine it, since the idler will change the rotation from clockwise to counterclockwise, and then clockwise to counterclockwise to clockwise, it will still have a clockwise direction. So the speed of shaft C is 100 RPM clockwise. And then finally, we have here a figure which shows a train in a cotton carding machine. So we are going to find the ratio of the surface speed of roll B and roll A. So the roll B is shown here in the bottom part, which has a diameter of 4 inches, and the roll A has a diameter of 2.25 inch, as you can see. So the compound gear train's velocity ratio can be computed by using our simple formula, which is just the product of the driven gears, driver gears, and the driven gears. So for the driver, if you are going to look at it, say for example, we have here the input at the roll A. So our drivers are the 135 teeth here at the top, and then we have the, so this is we have the 135 tooth here, and then we have the this is the driver. It drives the 17 tooth gear, and then we have another driver here, which is the 37 driving the 20, and then it is coupled to 130, which drives all of these gears here to come up with 26. And then finally we have 17. So this is the driver that drives 33 and another 33 here. So the drivers are the 135, 37, 130, and 17. So we'll put it here in the formula. The driven are the gears that are the output of each of these gear sets. So for the first gear set, we have 17 driven. The driven for the second gear set is 20. And then for the next gear set, this is another gear set. This whole thing here is another gear set. And the driven here is the 126. So the output would be, we would count the outputs, which is 26. And then for the shaft here, since we are concerned with B, the speed of B, then we will use the 33. So that's why we have here 33. So then we can compute the gear train's velocity ratio to be 37.84. So the surface speed ratio is defined as the speed ratio, it's just the velocity ratio of between roll B and roll A. So this is roll B here, and then we have roll A here. So the speed ratio can be written in terms of the angular velocity and the pi d. So we have pi d and multiplied by the angular velocity, would have the linear speed or the surface speed. So we can write it this way. And since we know that our MB or MV, our compound gear train's velocity ratio, is equals to the output over input, which is the angular velocity B over A, then we can substitute this one as equals to our MV. So we have here 37.84. We can cancel out the pi, and then we substitute the diameter of roll B and roll A, as you can see here, 22.25, and then we have 4. So solving, then we can get the surface speed ratio of roll B and A is 67.4. 27. So as you can see, the speed of roll B would be marked much larger than roll A because this is the ratio between their speed. So say for example, A is rotating at 101 meter per second, then our B is rotating at 67.27 meter per second. So this is another benefit of using compound gear trains in order to achieve the desired output speed. So for this cotton carding machine. So as a summary, we were able to discuss the fundamental law of gearing, the involute tooth form, gear tooth nomenclature, interference and cutting, the various gear types, and the gear trains, which are the simple, compound, and the planetary gear trains. So see you in our synchronous discussion.